Morning, welcome. So today I would like to talk about C++ dependency management with some statistics to get us started. So this is the number of packages in package repositories of a couple of popular programming languages. As you can see, when it comes to C++, before we can answer the question how many we have, we first need to decide which package manager we're going to talk about. As always in C++, we have several alternatives. I was told that the largest of them is apparently CppCon, and they have about 800 packages. So this second number in the Rust row is how many packages they had 2 months ago. So just think about it. In the last 2 months, Rust added almost 3 times as many packages as the largest package repository in C++ has in total. I think if this doesn't tell you that we have a problem, then I don't know what else will. So what exactly is our problem? Well, we have many, right? We don't have a standard build system, but that's for another talk on Wednesday. So we actually have a couple of package managers now in C++, but the problem is that they are what I would call consumption managers. Right? They can download, build, and install you a package and its dependencies, but they don't concern themselves with how those packages actually develop. And if you look inside, how the sausage is actually made, then the answer is usually painfully and rarely by mere mortals. And that's I think, the fundamental problem that prevents us from getting to thousands of packages in our repositories. We need to handle the entire project development lifecycle, starting from creation, development, testing, dependency management, of course, the central part, and as well as delivery, publishing packages to places where they can be easily accessed by the users. In other words, we need to turn every C++ developer into potential library author. So today I would like to show you, and there's no fundamental reason this should suck in C++, right? There's no reason we cannot do it. So today I would like to show you how we do it in build2. Which is a build toolchain for C++. So if you look at a language like Rust, they have a single tool. They have a model that I call a build systemless model, where you just interact with this package manager / build system. I don't think this is going to scale to C++, and it doesn't actually scale to more complex Rust projects as well, as they're finding out. So instead, build2 is actually a hierarchy of tools. So at the bottom we have the build system. In the middle we have the package manager, which is the consumption manager. Sometimes you just need to build a package. You don't actually plan to develop it. And then on top we have the project dependency management tool, which is what you're going to use to develop your projects. And this build2 toolchain is complemented nicely by your version control system, so together they will constitute the core of your development toolset. Okay, so we're gonna see how it works in build2. We need an example. Who wants to write another hello world example? No, not very enthusiastic. How about we write something real? How about we actually create a real library that most of us might actually want to use at the end of this talk? How about a portable, dependency-free UUID generation library? Currently, the only viable option is Boost UID, which is a good option if you already have a dependency on Boost, but to bring in this dependency just to generate UIDs sounds a bit of like an overkill. So that's what we're going to try to do. But before we actually dive in, let's step back a bit and talk briefly. How exactly are libraries developed? What actually makes someone create a library? Well, one possibility is, I woke up this morning, I realized, hey, I'm going to create this great new library. It's going to become popular in the morning, and I'll become famous, give CppCon talks. I think most of us by now develop a resistance to such marketing ploys. So instead, we would much prefer to use a library that was born out of real need. Someone had a piece of functionality in their project and they wanted to use it in another project, so they quickly factored it into a library. Or, I published my application, my program on GitHub, and someone saw it and said, hey, this thing it does nifty. I also want to do it in my application. Can't you put it in the library? So, and these are some of the properties of, or some of the guidelines when I use when I work on such organic libraries. They are normally, as I said, born out of a real need. They're usually small libraries doing specific thing, hopefully well. I also try to resist over-engineering things when I move a piece of code into a library, because now you're starting to base it on some theoretical thoughts. And I also like to have a test, at least one in my library. All right, so in this spirit of this organic library development, we're actually going to start with a program, with an executable, and then we'll see how easily we can factor this UID generation functionality into a library. So the easiest way, everyone can see, right? All looks good. The easiest way to create a project in build 2 is using bdep new command. So here we specify that the project type is executable, language is C++, so we're going to call it GenuUID. So this is actually going to be a fairly useful utility on its own, because there are usually utilities available on different platforms, but sometimes they're not installed by default, their format is different. Okay, so we've created just a second. So T is my alias for 3. So if we look inside, what we get is a hello world, a project which we can customize for our needs. There's also some build and packaging infrastructure set up, and I'm not going to spend half an hour explaining all of it right now. We'll just, as we need bits and pieces, we'll talk about them. Now, this is also a good time to talk about build systems briefly. If you look at Rust, for example, they have what I would call a build systemless model, right? You put things in certain place, name it a certain way, and then you'll get an executable or a library. I don't believe this is going to scale to C++ requirements, and we'll see a good example of that in a few minutes. But what we can actually, kind of even by accident, we achieved in build 2, for simple projects, you can actually approximate this build systemless flow. If you put your source files in this project subdirectory, in the source subdirectory, you can add new source files, you can rename them, you can delete them, and the build system will automatically pick it up. You actually don't need to touch the build file when you're just adding or removing source files. So I think this is kind of a nice middle ground. For simple things, you rarely need to touch the build system, but if you need it, it's actually there. And we will see now, quite often you do need it. Okay, so there is our source file. We can already see it. But before we're going to go hack on it, let's first set up build infrastructure. So in build 2, we build normally out of source in directories called build configurations. And so we need to initialize our project in a couple of build configurations. Normally in C++ we have several, at least, different compilers, options, and so on. So we're going to use the init command. So with init you can initialize a project in an existing build configuration, but we haven't created any, so we're just going to use its create mode. So here we gave it a name, GCC, and we are using the GCC C++ compiler. Yeah, just need to go inside. So yeah, this is actually a good point to make. The workflow of bdep is made to match the workflow you'd normally, the development workflow that is dictated by your version control system. So normally you do things from your source directory of your project, so build 2 kind of doesn't try to change the way you do it. Okay, so here's one for GCC. Let's do also for Clang. I have Clang on my machine. Let's also do, for interest's sake, to keep things interesting, let's also do a MinGV. So MinGV is a cross-compiler. It's a GCC for Windows, right? So now if we look at the parent directory, so next to our project, we have the 3 directories appropriately named that contain our build configurations. Okay. Another way to check what we have, which build configurations we have with bdf config list command. So they are those 3 again, they are their names listed. You might notice that the first build configuration is a little bit different, has a little bit different properties. So in build 2, one build configuration can be designated as the default, and this has a couple of nice properties. If you run the build system in the source directory, then it will automatically build in this default build configuration, so you don't actually need to specify the directory explicitly or change the directory. And also some interesting targets, for example, executables, documentation, test results, they will automatically be backlinked into your source directory. So you can, for example, easily run them. So let's see how that all works. So there we ran the build system, directly now sourced. And if we look at the listing, there is our executable, which is actually a symbolic link to the executable in the default build configuration. We can even run it. As promised, it's a hello world example. It's also building all other build configurations that we've set up. We can do it with the build system directly. We'll just have to specify the long directory path explicitly. A more convenient way to do it is with bdf update command. We can use the Clang. We can use names that we gave our build configurations, for example, Clang. Or we can say update all build configurations, quite a handy option. So there the GCC was already up to date and the other 2 were updated successfully. Okay, so there is our build infrastructure set up. Now we are ready to start changing our hello example to actually generate UIDs. So again, there is our listing. So we see the source file, so without much thinking, let's just go and start messing with that. So there is a hello world example. The font is a bit small, right? You cannot see, correct? Just adjust it. Okay, a bit better. Okay, so the hello example as promised. So I'm going to replace it with my UID generator. As you can see, I type very fast today. I'm not going to go into too much detail. There is the type UID that has a generate function and has a string function, which is what I use in main. And then at the bottom there are the gory details, right? How we actually do it on different platforms and so on. Okay, so let's go try to build it. Run our build system, so it compiles successfully, but then the linking fails. So it turns out that the system function that we actually use on Linux to generate UIDs, it requires us to link a separate library. This is a good example where a build systemless model only takes us so far. Right? We actually do need the build system, we need to link this library only on this platform. So we have to go look at this build file. Okay, it's short, a little bit cryptic. I'm not going to go into detail on this today. There is nice documentation if you are interested. So I'm just going to link the library. So there we link it for Linux, and I'm also anticipating some issues on Windows, so I've fixed that as well. Okay. Try to run the build system. Okay, so that worked. It even generates us some UIDs, and they're even unique. Let's try to run tests. That didn't work out very well. Well, if you look at the diagnostic, it kind of makes sense, right? It was originally a hello world example, and now it generates UIDs. So let me also fix that. So there are two types of tests in build 2. There are simple tests, you make an executable, and if it runs successfully and assumes the tests have passed. There are also scripted tests where you can analyze input, supply input, analyze output with regular expressions and so on. And they also run in parallel quite nicely from the same file. So again, there's a nice documentation for this. I'm just gonna replace it. So there are two tests. First checks that the format is correct using a regular expression, and the second one just generates two UIDs and makes sure that they are different. So just basic smoke testing, but good enough for our needs. Okay, let's try to run the test. So the test succeeded, just got a warning that the directory had some stuff in it from the previous failed build. To test other build configurations, we can use similar to update, there is the test command. We can just do test all and test in all build configurations. Even the Windows test succeeded, so if those of you are wondering, this test is running under Wine emulation. Okay, I think our little tool is in a good shape. Maybe we should commit it and push it to GitHub. Before we do that, though, let's briefly talk about you're referring to the test warning, right? Well, it does that. It just warns you that there was some stuff there for safety reasons. Okay. So versions, right? So before we actually publish anything, let's briefly talk about versioning. So versions are a signaling mechanism, right? They tell our users what kind of changes they can expect to find in each release. Right? I'm sure most of you are familiar with versioning, and the development world pretty much standardized on semantic versioning. Yes, it's not perfect. Yes, it has issues, but it seems to be the tool that does the job most of the time. So there are different ways to map it to C++. We have binary compatibility. We have source compatibility. The mapping that I prefer and recommend is to reserve patch versions for binary compatible changes, and mostly specific bug fixes. Use minor versions for source compatible changes, and if you're not sure what exactly the effect of your changes, just be safe and increment major. Hopefully there will be tools that will actually suggest or check for us which component we need to increment. So if anyone wants to work on such a tool, I would gladly use it. Okay, so it's easy so far. I'm sure I haven't told anything new to most of you. So there are two releases, right? What happens in between? What if we want to publish an alpha or beta release for our users to test? Well, it's actually handled by semantic versioning, so there can be a pre-release component. So there we have our first alpha release. Right? Okay, what happens in between? What if we want to publish our version to a CI server, or some of our users wants to test a specific commit? For example, we implemented a feature for them and said, hey, test it for me. How do we communicate? We can specify commit ID, but that's not exactly the same. If you don't change a version for each commit, you might have the same version that signifies multiple states of your project. And that actually can be painful. So in build 2, what we have is called continuous versioning. So in build 2, every commit of your project is assigned a unique, properly ordered version. So this is what it looks like. So for releases, pre-releases, nothing new here. So those you manage yourself. But in between, for unreleased commits, the build2 in cooperation with your version control system automatically assigns you a snapshot version. So this is what it looks like for Git, for example. So it's a commit timestamp plus an abbreviated commit ID. Let's actually see how it works in reality. This is all theory. So if another handy command is status. So if we run bdep status, it tells us what is the status of our project in a build configuration. In this case, it's the default build configuration because we haven't specified one. So this version doesn't look exactly as what I've shown in the slide. The reason for that is because we don't have any commits, right? So if you don't have any commits, you get this special Unix epoch version. So let's go ahead and commit. Make a commit and run status again. Okay, so the configured version is still the same, but now we have a new available version. So this is the example of where the build system noticed, okay, it queried the version control system, your Git in this case, and saw that there's a new commit and it assigned a new version for us automatically. So this is important. I believe for this to work practically, it has to be automatic. You cannot be going and modifying your version file every time you make a commit. Nobody's going to do that. Okay, so if we run the build system now to update our project, well, the last line says that everything is up to date, which makes sense. We haven't really changed anything. The first two lines are actually what I want to draw your attention to. What we have here is automatic synchronization on build system invocation. So in build2, if a metadata of a project, for example, its version or set of dependencies changed, then every time you invoke the build system, these changes are detected and automatically synchronized with the build configuration where you are building. So this might not look very interesting. After all, nothing changed, but we'll see in a moment where it does make quite a big difference. Okay, so we've made a commit. I'm gonna go and create a repository on GitHub in my personal account. I'm sure most of you have done that before, thousands of times. So there's a new repository. I'm going to go and add a remote and push my changes. Okay, there they are. Nothing new, I hope, for most of you. So now our little utility is published, people can use it. There is, however, one issue. So we kind of called it portable, but we haven't really tested on that many platforms and compiler combinations, right? We've tested on Linux, and we've also tried it with GCC, with MinGV GCC for Windows, ran it on the Wine emulation. But there are also Mac OS, there's also Visual Studio on Windows, there are also things like FreeBSD and so on. We could test this manually, right? We can use some virtual machines. For Mac OS, you would need real hardware, but that would be quite painful and tedious, and especially it would be unfortunate if we don't ourselves care about this platform. So if I don't care about Mac OS or FreeBSD, I'm probably not going to do it if it's painful. So in build2, we actually have a better way to do it. So in build2, we run a public CI service for open source projects. So we can actually test our project on all the major platforms and compilers without actually leaving our preferred development environment. So let's see how that works. So we use the bdep CI command. So what it does, it sends this specific commit, this specific version of our project for remote testing to the CI service. Let's say yes here. So in return, we get a link, a URL, which we can go and take a look at the build results. Okay, so it's already started building. So if we refresh the page a couple of times, we'll see more builds, hopefully. So we can go take a look at what build configurations are available. So currently we offer basically all the major mainstream platforms, Linux, Windows, FreeBSD and macOS, and the latest 2 versions of main compilers for each of them, so Visual Studio, Clang, GCC. We also have some interesting combinations, for example, a Clang with libc++ on Linux, or Homebrew GCC on macOS, and there's a MinGV for Windows. So I think this gives you a pretty good coverage for general purpose platforms and compilers. Sorry? Not yet, maybe in the future. Okay, let's go back to our build. So there are actually 12 build configurations in there, so you can see some of them are still building, some of them have finished. So let's take a look. Okay, there's actually an error for Linux, on Linux, which is a bit surprising. We kind of tested it, it was our development machine. So if we go look at the logs, so what happens is the header that we include, it actually comes from a separate package that is not installed by default. So the platform that we probably the most sure about turned out to be actually not such a great shape. Oh well, some surprises, right? Let's take a look what else is there. Well, the pleasant surprise is that it works out nicely on macOS. Right? Everything built successfully. What else there? FreeBSD also failed. If we go look inside, the same story, except here we don't actually have a package. You know, this header just not available on FreeBSD. There's a completely different API that you use for generating UIDs. Let's also take a look at Windows with Visual Studio. Okay, so that looks good. So there's a Visual Studio 14 built successfully. We wait a little bit longer. Yeah, there's a Visual Studio 15 also built successfully. All right, somewhat a mixed bag, right? The platform that we were most sure about, you know, turned out to be in pretty bad shape, but otherwise, some other pleasant surprises. And I think that's okay. I think if we adopt this organic development mindset, it's fine. I published my project, someone can come, and if they're interested, they can come and help and improve it. Well, speaking of help, let's say someone saw our project on GitHub and they want to join the project, you know, help us develop it, maybe fix some issues. So one of the key goals of Build2 is to provide a uniform interface and consistent behavior across all the platforms and compilers. So let's see how that actually translates to reality. So here, let's say our collaborator is actually on Windows, right? They're using a Windows for development. Let's see how difficult it is to actually for them to get started. So this is the proverbial, you know, git clone and now what question, right? I want to clone and get to hacking as quickly as possible. So there is my clone. So again, we use bdep-init to initialize and create configuration all in one go. Let me just find it in history. There it is. And there it is. We can even try to run it. Generates even the test work. All right, so that wasn't, I think, too painful. It probably took me 30 seconds to get going. Okay, so I think we're in not a bad shape. Some platforms don't work, but hopefully someone will help fix us that. So now let's say we want to generate UIDs in another project of ours, right? So now is that part where we take this functionality and put it in the library. And this, I think, is a critical path, again, to achieving these thousands of packages, and making everyone a library developer. If this is a 5–10 minutes process, fairly painless and frictionless, then, I might create a couple of libraries a day. There's no issue with that. But if instead, as it is now, it's a multi-day, painful process of testing things in different places, different ways, then I might as well just duplicate the code. Yeah, there will be a maintenance headache, but it's going to be later. It's not going to be now 2 days of pain. So let's see how that all works out. Again, we use the new bdep new command to create new project. Instead now, when executable, we say it's a library, right? So the type changed to a library. I'm calling it libstud_uid. So I'm working on a family of small libraries called libstud. The name is a play on the pronunciation of namespace std. So the joke here is that most of these should have been in the standard library long ago, but let's not go there. Okay, so there we ran it. If we look at our directory, there's our executable, right? There's the 3 build configurations, and there's now our library. And if we look inside, again, it's a hello world library that is ready for us to be customized to suit our needs. A little bit more infrastructure there, but otherwise it's pretty similar to an executable. Before we start modifying it, let's again set up build infrastructure. This time we're just going to reuse our existing build configurations, right? There's no reason for us to create new ones. So we're going to use the add mode of bdep init. So there's gcc, there's clang, and there's min_g. Just to make sure everything is good, let's build and run everything in all build configurations. Right? bdep test all good. Okay, so now is the point where we take the functionality from our executable and put it into a library. I'm not going to do it live. I'm just going to copy the code over. It turns out, it was somewhat surprising to me, that generating a UID portably on different platforms is actually more difficult than one might think. In fact, on many platforms you might end up with a non-unique UUID, so we need to handle that situation. So let me take a look. So there's our source files. You can see there's some platform-specific source files. There's a Linux one, maybe hopefully miraculously fixed our Linux issue. We just again build and test it locally. Okay, all works good. I'm going to now commit it. I've already created a repository on GitHub, so I'm just going to add the remote quickly and push it, and we're going to CI it again to see what's going on. So again, sending it for remote testing, getting a link back. Let's open it in a browser. Let's see if it starts building. Okay, so the build went off. While we are waiting, so it'll take a few minutes, let's go and start adjusting our GenUID utility to actually use the library. Right now, so we just copied the functionality. It doesn't make sense to have it in two places, so we're just going to add a dependency on the library instead of having it there. I'm going to go there. There's our listing again. So first place, let's start with a source file. Right, so this one I'm going to do live. Leaves the namespace stud, but otherwise the same interface. And I'm going to remove the gory details. So now our little utility is nice and clean. Right? Okay, so here they included, and we called all the functions. So we need to link the library somewhere. So again, our build file. The generated build file actually includes some commented out infrastructure for importing libraries from other projects and linking them to our executable. So we're just going to use that. So this is, we imported it, assigned it to this libs variable, and there it's listed as a prerequisite of our executable. So again, nice thing is that we can get rid of this ugly explicitly library linking. So now our build file is nice and clean and simple again. Okay, so here they included library linked. Good question. Include? Yeah, those I need. This is for the executable. How you include here this in the executable. Again, documented and explained the rationale in documentation. Okay, so here they're included, library linked. Where will our library come from? Well, natural place from a package. Right? So we're going to go and list a dependency on a package. So the place we do it is in the manifest file. So manifest describes your build system project as a package, right? So at least name, version, some other meta information, license, for example, which we can fix while at it. So there is again commented out suggestion how we might want to do that. We're just gonna follow along. We're gonna remove the version constraint for now. We'll get back to that later. Okay, so here I included library linked package dependency setup. Where do packages come from? Package repositories, right? So that we specify in the repositories.manifest file. Again, a couple of commented suggestions. One of them is looks like a Git repository, so we're just gonna play along, right? We'll just put a GitHub repository of our libstudy UID. And, let's use the version that are available from master for now. Okay, so some of you, even to me, having to specify this in 4 different places might sound bizarre, right? But there's actually good reasons for that. They're quite technical. But in a nutshell, it's flexibility and not having to repeat yourself in multiple places. But again, it's all explained quite well in the introduction. At least I think so. As I think the recurring theme, in C++, we have special needs. Okay, so there we've converted our project to use the library. Let's go take a look at our build results. So they're all 12 build configurations built, and they're all green. So even the Linux issue miraculously disappeared somehow. So actually, the fix is actually quite interesting. So if you are curious, you're welcome to go take a look at it, or find me after the talk. I'll tell you how it's done. Okay, so our library is actually in quite a nice shape, which means that our utility will also be nice and portable, as promised. Let's try to build it. So there's quite a lot of output. So again, auto-synchronization kicks in, right? We've added a new dependency, meta information about the project changed, so it's automatically synchronized with the build configuration that we are building. So there you can see the packaging information is being fetched, things got upgraded, and so on. Let's also run tests in all other build configurations. So now that we have a dependency, we can run tests for our own utility, but it might actually make sense to run tests for our dependencies as well, seeing that we are using them. So we call it deep testing. So all we have to do is just add the recursive, to test recursively option. So there you can see both tests for the library as well as for our utility are executed. It's also quite a handy thing. When things are nicely integrated, you can run tests on all your dependencies. Okay, let's commit and push. I'm also gonna start the CI process just to make sure everything is in good shape. Notice that I don't need to worry about, will the CI process find my dependencies and so on. So this is all taken care of. So there the build started. Again, while we wait, let's go see how our Windows collaborator is doing. Now, this is a good example of where auto-synchronization is important. It would be really painful if I have to keep track of, what changes to the meta state of a project happened, on each pull and do something manually. So in build 2, all we have to do is pull and build. We don't have to worry about it. Auto-synchronization kicks in. So in this case, we're actually getting a library installed and built, downloaded, built and installed. Well, not installed, but to be used by our executable. So again, this process was rather painless for our friend here. Okay, let's take a look at our CI. So if we wait long enough, they will all be green. The FreeBSD is happy now. Linux as well. So now we actually have a fairly portable UID generator and a library. Okay. So we published a library to our GitHub. So how will people find it? Some potential users. Well, again, you can go to GitHub and search for UID library or UID generator. You'll get a couple of hundred results. Most of them are not even C++. And I think this is a good example. It will actually miss the most promising option, well, before we just published this library, which is Boost, right? If you go to GitHub, you won't find Boost there. And I think experience of other languages that are ahead of us on this field, like Rust, for example, shows that it's really useful to have a central repository of packages, an archive repository of packages. In fact, it's quite useful to have both. They in a sense complement each other. So it's nice to have version control-based repositories and archive-based repositories for your package manager. So version control-based repositories are great for development, right? They're trivial to set up, 30 seconds on GitHub. Also your project repository, at least in case of build 2, is normally your package repository. You don't actually have to create anything else. And this is exactly how we've done it with our utility and a library, right? Remember when I put this link to GitHub URL in the repositories.manifest file, I used the libstd-uid Git repository as its package repository. So very convenient. There are problems with version control-based repositories. As mentioned, packages are hard to discover. There's GitHub, GitLab, all other different hosting places, so you'll have to go look at all of them. They're also not very reliable. Users might decide, I'm going to delete this repository, and your program depends on it. Also, hosting companies, can go out of business, can get acquired. Version control repositories are also not as secure as archive-based repositories can be. In case of build 2, a repository is authenticated and packages in the repository are signed. So it's pretty difficult to tamper with. We'll see an example of it in a bit. Finally, version control repositories are pretty slow for creating the list of available packages. You, in most cases, have to clone actual content, and this especially becomes painful when you have for example, 100 dependencies, each living in its own package repository. And I can spend 15 minutes just querying the package information. Okay, so as you can see, the two types of repositories actually complement each other quite nicely, and our recommendation is to use your version control repository for unreleased packages. Like for example, implement a feature for someone, and you say, hey, you know, there's a tag or there's a branch, go check it out. And they can just use it as a package, as a package repository. But at the same time, you would want to publish released versions of your project into an archive-based repository. So for build 2, we run a central repository on cppget.org. You're free to run your own archive-based repositories. Like for example, if you want to have one internal in your company or even a public one, alternative to this one, you're welcome to do that. So let's just go take a brief look what it actually looks like. So if you go to the front page, now we get a list of packages, and we can use a search box, for example, to search for a hello library. There we get a couple of results, and they immediately get some information that is useful for you to make the selection, which one you prefer to use, for example, license and number of dependencies. And once you narrow it down to a package, you can go and see which versions are available. Again, they're in different sections, like some, for example, can be in stable, some in testing, so you can decide which ones you want. And if you go to a specific version, then besides even more information about it, you see, for example, all the build results for this version. So you can actually check, you know, if you need Windows and this package fails to build on Windows, it's probably not a good idea to use. Okay, so there's cppget. So as an example, let's let's make a release of our library and publish it to cppget.org. Again, ideally we would want this process to be as frictionless and painless as possible. So the only place we're gonna need to change the version is the manifest. It propagates from there everywhere else. So as I mentioned, release versions you manage yourself. There's no any kind of automation or messing around with it. No, huh? How did I get here anyway? Okay. Okay, so we just changed the version and now we are good to commit our changes. Also gonna tag it. So we use this form that is quite adopted by quite a few projects. This notation v and then the version. So this tag now that we're gonna push it now. So now the users of our package can actually use our GitHub repository, and instead of master, for example, as I shown in the repository URL, they can specify the version if they prefer this specific version, for example. Okay, if we're pushing it. Okay, so now we've made the release, published it, tagged it in our GitHub. So now we want to publish it to cppget.org. So this is automated with the bdf publish command. So in a sense, it's similar to CI in its workflow, right? It's submitting our package for inclusion into archive-based repository instead of testing. So provide some information, you know, who is submitting it and so on. So we're gonna say yes, there's some more information being printed. Some things got uploaded. So it creates an archive of our package and uploads it to submission service. Tells us that the package submission is queued and give us a link where we can go take a look at something. Before we do that, let's briefly discuss what happens to a package once we submit it to an archive-based repository. In case of cppget, we're trying to strike a balance between a large repository of low-quality packages on one hand and a repository of a few packages of high quality on the other, but the submission process is so annoying and painful that nobody bothers to submit to that. So what we came up with is a rule of one. So we don't review packages. We don't decide whether it's worthy to be included. So provided a package satisfies these simple rules, it's going to get included into cppget.org. So once you submit a package, it gets into a queue. So it's a queue section of the repository where it's tested similar to CI, and provided that it builds on at least one platform and compiler, it's going to get moved to testing. So the rationale here is that if it builds on at least one platform and compiler, then it can be useful to someone, right? If it doesn't build on anywhere, probably no. So once in testing, it's going to be tested on a bit more compilers and platforms. So we also build on with all the versions of the compilers. So if you want to support those, you can see what's the status there. Also, the users of your project, they have a chance to test things against their projects. For example, if they depend on your library. So provided there are no issues there and your project has at least one test, then it will be moved to stable. So again, here we require you to have at least one test, and I think it's a reasonable expectation, because think about it. If you build a library and you actually, and you don't have any tests, you don't actually know whether your library links, right? Let alone run. For example, for me personally, it's very common to forget to export symbols from a library. So if you don't even try to link it, then, you cannot really say anything about it. It's also possible that a package is no longer maintained, package version is no longer maintained, and it fails to build on all the platforms and compilers that people can reasonably care about. So once a package is unstable, we actually never remove it from the repository. So that's the reliability guarantee that I mentioned earlier, but we might move it to the legacy section where we stop building it, right? So if it's no longer maintained, then new projects probably shouldn't depend on it. Okay, so with that understanding, this message is probably now makes more sense. So we get a link to the queue section where we can see our package. There it is, has already built, as you can see, in all green. So, it will sit there for some time and will be moved to the testing section, sit there for a little bit longer, and then will end up unstable. So I actually went through this process a couple of days ago, so we don't have time to wait. And I published the library to cppget.org, so it's actually already available in the stable section of the repository. There it is. So just as an example, let's go and add a dependency, add this new repository to our executable. And we'll also add a version constraint to our dependency. So again, we will uncomment the suggestion. So as you can see, even the link is already actually contains the cppget.org stable section commented out. So if you want to use packages from cppget.org, you just need to uncomment this. There's also the trust field. So this is that repository authentication I mentioned earlier. So if we don't specify the fingerprint there, then we'll be asked to manually authenticate the repository every time we build things, which would be annoying. So in a sense, we're establishing a chain of trust here. As you can see, I still kept the Git repository as a source of this package, because in case if I want to test some unreleased version or some such. Let's also add a dependency constraint here. Now that we have a stable version released, just briefly about dependency constraints. Okay, so those of you who've used other package managers probably are familiar with caret and tilde constraints, right? The caret constraint is any major, later major or patch, minor or patch version, and tilde constraint is more conservative, only allows new patch versions. So the caret constraint is a good default. There are also other operators and ranges, so we're just going to use that. Right. So we specify, we are happy with any later version as long as the major version stays long, which means it's source compatible. Okay, we're gonna run tests again, auto synchronization, things would get pulled out, all looks good. Let me also commit this change. Just want to go see how it is on Windows, how this will all play out on Windows. Let's go take a look there. Again, it would be, now that we've placed a version constraint, the version that we have built on Windows early, it no longer satisfies this constraint, right? So again, it would be unfortunate if we had to do anything manually there, but luckily we don't. Again, automatically synchronized, and our old version, as you can see, is automatically upgraded to the latest one. So again, pretty painless experience. No, sources, all sources, no binaries. So this is a source-based package manager. Okay, and that's pretty much it. Just to summarize quickly what we've done. So we started with an executable. We then factored the UID generation into a library, fixed it up, so now it's nice and portable. We then made a release of a library and published it to an archive-based repository. Right? And just to summarize key points about build 2, I think the overall theme is that development in C++ doesn't have to be painful. There is no reason why we cannot do as good or even better as Rust. Like, for example, some of the things like continuous versioning or the CI service, it's something that you actually don't find in Rust, and I think it's an improvement over their model. So just to summarize, it's integrated build toolchain for C++, so package manager and project dependency manager and build system, they all, their design informs each other. It covers the entire project development lifecycle. It has a uniform interface across platforms and compilers. Supports both archive and version control based repositories, which is really handy. They complement each other nicely. Finally, it's dependency free. All you need is a C++ compiler. So, and this brings me to our offer to the C++ community. So, start new projects or convert your existing projects to build 2, and you can CI them for free on all the major platforms and compilers. Right, so this is what's currently available to you, and we are also planning. So we'll keep upgrading. Microsoft release new version, Clang release new version. You don't actually need to do anything. We will keep upgrading these machines and make them available to you. Also planning to add some static analyzers and sanitizer builds as well. We actually have them locally already testing, but haven't pushed them to CI. And additionally, so you can use the CI service even if you don't publish anything to cppget.org. If you do, then you'll get some additional testing. We also test there for all the compilers if you want to support that and so on. Okay. Thank you very much. Okay, we have a few minutes left, but I'm happy to stay. So someone had a question. Well, okay. So the question was, how do I build debug or release versions? Is there some command line argument? So you've seen how I've created the build configurations for Clang, GCC, and MinGV. So you'll do it exactly the same. You can create 2 build configurations for GCC, one debug, one release. So the question is there an easy way to consume libraries that don't use build to, such as autoconf-based or automake-based? Yeah, the answer is yes, especially if your library produces pkg-config file, like, as most autoconf libraries do. It all works automatically. So to put it another way, the way to interface with other libraries that use other build systems is by installation. So you install them, not necessarily into your system location, but somewhere, and then, even if they don't provide pkg-config file, they will, it will still be usable. But if they provide pkg-config, then build to will automatically use that.
So the question was, can the library which is not the part of a build system become the part of the repository
Okay, so the question is it possible to upload or submit a library that does not use build to the repository? And the answer is no, and the reason for that is it's just not going to work. We won't be able to build it.
And last question
So
is...
let's maybe come around. Can we skip?
So, just a quick question. The consumers of the packages describe their static and shared requirements. So you grab the library and build it, but what does the library say it needs to be static, or does the consumer say, I want you to do that when you get them?
Okay, so the question is who can, let me see if I got that, who can dictate whether the library is built static or shared, or maybe both? And it's actually both. So you can, it's not very common, but you can, for example, say my library only builds static or only shared, but also consumers can specify priority in which one they want to link. So it's both ways in a sense. Okay. Sorry? RPaths. Oh, okay, good question. So the question is, do we handle RPaths? And the answer is yes, and we go actually a step further and we emulate RPath on Windows, so you can actually run the executables in place. You don't need to stash them in a bin directory where your DLLs live, and end up with conflicting names and so on. So yeah, we do. Okay. So I think we are out of time, but yeah, I'm welcome to stay and answer questions. Thank you very much.